Hello mathematicians, puzzlers, and other curious people. In this video, we are going to take a look at how math is used to deal with motion, specifically motion of an angular around a circle, so on an arc type of a variety. So let's take a look. In this problem, we see that Cassidy's bike does not have a speedometer, but she knows her average cadence, which is a technical term from cycling for her revolutions per minute on the pedals, is 76. The gear attached to the pedals is 6 inches wide, and her bike's back tire is 30 inches wide. When she is using the gear attached to her back tire, which is 2.5 inches wide, what is her speed? Now, on this problem, it's kind of tricky because we've got a lot of information. One thing that's always a good idea when you have a lot of information to organize is to set up some kind of a table or a diagram. And in this case, the diagram that I'm going to use is literally a picture of a bike. So let's translate this problem statement into information we can use to solve it. So I see that her average cadence is 76 revolutions per minute, and the gear attached to the pedals is 6 inches wide. We're also told that her bike's overall back tire is 30 inches wide. And she's using the gear attached to her back tire, which is 2.5 inches wide. What we would like to know is the linear speed of a spot on her tire as it goes around and makes contact with the road, and therefore the speed at which her bike pushes the road, so that the road pushes the bike also at that speed. The only rate we know right now is a rate of revolutions per minute, and usually when we talk about the speed of an object, we want to end up with something like feet per second or miles per hour that's easier for us to think about. So here's one thing I notice. I notice that we always have this fact that if you take an angular motion in radians and put that over 2 pi, and then multiply that by the circumference of the circle, so good old 2 pi r, then you'll have the linear speed of an object that's moving along that arc. But one thing you might notice about this formula is it's a bit repetitive. We've got dividing by 2 pi and then multiplying by 2 pi. We can simplify that and just say, okay, take that angle in radians and multiply it by the radius, and we will have linear speed. Okay, sounds easy, but we need to know 76 revolutions per minute as an angle. Well, here's what I know currently, that there are 76 revolutions in 1 minute. I'm keeping my units with me really carefully because I suspect I'm going to need to do some unit conversions later to get this into units that are convenient to wrap my mind around. So I see that as part of my unit conversion process, I'm going to want to cancel the number of revolutions, and I know that each revolution is 2 pi in radians. And radians aren't really a unit, but when you're working with unit conversions, it's a good idea to keep track of them anyway. So now I see that we've got matching units of revolutions. I see now that the angular distance traveled by a spot on that gear that's going around and being pedaled would be double 76, so 152 pi in radians per minute. So what we have here is an angular speed because we have a distance being traveled that we've written in angular format on the arc, and we have the amount of time it takes to travel it. And remember, anytime you've got a distance over a time, what you have is a rate. But of course, we should keep in mind we wanted the speed of the overall bike, not the speed of a single link traveling around that gear. So how do we get from that to that? Well, we can look at the bike to see how we get from that. What connects this gear with this gear? Because then this gear turns this wheel and moves the whole bike. Well, it's this chain that connects them. So this chain is going to have the same linear speed all over. As we're pulling this chain along, it's going to turn this gear by the same linear amount. So we need to find out what that linear speed is using this linear speed formula. So we'll take pi times the radius. Well, what's the radius? We know the diameter is 6 inches, radius must be 3 inches. That works the usual way. So now we can take what we know, that what we have is an angular rate of 152 pi in radians, and that's still happening in 1 minute. And then we take that radius, 3 inches. Although radians are not strictly speaking a unit, when you do a unit conversion where you're dealing with a radius, it acts a whole lot like a unit. So now what we have here is an excellent calculator problem, because in 1 minute, we're traveling some multiple of pi inches, and that multiple is going to be 3 times 152. That's not a mental math problem. So I'm grabbing a calculator. So I see that that is 456 pi inches per 1 minute. Now remember, that's not the speed of the bike. That's the speed of the chain. A very common mistake in this type of problem would be to stop too soon. What we know now is the speed of the chain. What we want to know is the speed of the bike, which is the linear speed of the outside of this tire. We can get that using the angular speed as a middle step of the tire, which is the same as the angular speed of the gear that's attached to the tire. So I see that the gear that's attached to that tire is 2.5 inches across, which means it has a radius of 1.25 inches. So currently we know the linear velocity of the chain, and therefore of that gear that the chain is attached to. That is 456 pi inches in each 1 minute. Since we would like to get that back into angular format, I would like to get rid of these inches. Well, how can we get rid of inches? By reintroducing the radius. So that radius is 1.25 inches. Why did we reintroduce the inches? Because that way we can eliminate them from our calculation the usual way for dimensional analysis. From there, the next thing we can do is just multiply across, again, the usual way for dimensional analysis. So this angular velocity now, because we've reintroduced that we're in radians, will be 456 pi in radians per 1.25 minutes. But that's not a particularly useful unit, so one thing we can do is get this back into single minutes. By dividing out just a scale factor of 1.25. Now, you have probably heard it said that when you're dividing fractions, you need to invert and multiply, and that is one way that works when it's necessary, but when the numbers happen to be compatible, it's okay to just divide across. Now, I don't know if these numbers are completely compatible, but I'm not going to fret if we fall into decimals. So I see that 1.25 divided by 1.25 would be 1, and I know that this will be some multiple of pi and in radians. I just need to know which multiple by saying, okay, 456 divided by 1.25. And again, that seems like an excellent calculator problem. My calculator informs me that that is 364.8. So now we have that the angular velocity of this gear right here, and therefore because of the spokes attaching it, this tire right here is 364.8 pi radians per minute. But now we need to get that back to linear speed, and we'll do that using the same formula. So 364.8 pi in radians per minute will get multiplied by the length of the radius to eliminate that inconvenience. Well, what's the length of the radius? Well, I see that the diameter was 30 inches, so certainly the radius will be half that, 15 inches. And then, again, we've canceled our units that we can, so then we just multiply across. And I see that our time in this rate is 1 minute. And our length in this rate is going to be some number of inches, and it will be some rational constant multiplied by pi. That rational constant will be 364.8 times 15. Again, excellent calculator problem. And I get from that 5,472 pi inches per minute. Now, it's a good idea in these in general to go ahead and take it to something that, even if it's approximate, is just written as a number instead of with a pi in it, because it's hard to visualize pi. So let's see. Times 3.14159, and again, it's an excellent calculator problem. That is 17,190.78, and of course it continues because pi, but I'm just going to cut it off there, inches, because I really believe that anything less than 1/100th of an inch is trivial in this context, per 1 minute. Now, if the result you need is in inches per minute, you can stop there. On the other hand, if the result you need is not in inches per minute, you would need to know how to do a little more dimensional analysis to get this into the units you want. So I'm going to start with these units that I have right here. 5,472 pi inches per 1 minute. And I'm going to get that into units that I think about speed in, which is miles per hour. Some people prefer kilometers per hour. Depending on the problem you're doing, you might need to put it in seconds instead of minutes even. Whichever way you need to convert it, just use things you know about ordinary unit conversions to set up some fractions to multiply by. And that's the key idea of dimensional analysis. So I want miles, I have inches. Well, I know that 12 inches would be 1 foot. So here I'm setting up a unit conversion fraction of 1 foot over 12 inches. And since 1 foot is 12 inches, that's just a fancy way to say the same thing over the same thing. I'm just saying t for thing, it wouldn't matter. Well, that just equals 1, and when you multiply by 1, it doesn't change the value. So I'm not really changing anything here, I'm just changing how I say it, but I'm not changing the actual amount. But I didn't want feet, I wanted miles. So I know that 1 mile is 5,280 feet. And now I see that that's going to eliminate the inches that I didn't want, eliminate the feet that I didn't want, and bring me to the miles unit that I did want. So now I'm done dealing with the length conversion factors. So now I'm going to look at my time conversion factors. I'm in minutes, I want hours, that is easy. 60 minutes is 1 hour. Again, it's just the same over same. Unwanted minutes cancel, And again, this is just fraction simplification, numerators and denominators. Now, these are almost always excellent calculator problems. I see that I am ending up with my unit being miles, and it'll be a multiple of pi to keep it exact, and that multiple of pi will be whatever 5,472 times 60 is. And that is 328,320. And then in the denominator, I see we're in hours. And that number of hours will be whatever 12 times 5,280 is, which is 63,360 hours. So now I know at this speed, 63,360 hours would result in a trip of 328,320 times pi miles, but I'm not interested in keeping going that long. I just want to know about 1 hour. So divide out the unwanted scale factor. And again, we're just taking the same thing. I'm doing S for same over S for same, which is equal to 1. Dividing by 1 doesn't change the value. However, I see that I'm a little short on space, so I'm going to bring this over here through a miracle of technology, and then continue. So I see I'm dividing. I see in my denominator I will get 1 hour. Not a coincidence, I meant to do that. In my numerator, this is definitely an excellent calculator problem. So I'm grabbing my calculator and I'm punching in 328,320 divided by 63,360. And I get 5.18 repeating, so 5 and 18/99ths, and yes, we could simplify that. We don't care right now. But 5.18 repeating, still in pi miles. Now at this point, again, it would be useful to change that to a little bit easier to look at kind of a number, like just a decimal with digits. So I'm going to go ahead and multiply that by an approximation for pi, 3.14159. And I see that this is about 16.28, again rounding to 2 decimal places as I have been, miles per 1 hour. Okay, now because this is a believable speed, 16 miles per hour on a bike, I think this probably went correctly. So I'm going to say that this right here is my answer. If you need to put this in someplace that needs an exact answer but won't take that repeating notation, just do a little side copy. Let's see, 18/99ths. So you've got 2/11ths. Well, then add the 5 back in. So you'd have 55 and 2, so 57/11ths pi miles per hour. But for most practical purposes, I prefer this form right here. Okay, so that's all there is to it, and that shows a few times over and in a couple of directions how you can convert at will between angular and linear velocity and how those go together in some real-world types of problems. Calculator!